The resistance of the ground path is a crucial factor in determining whether a circuit breaker will trip during a ground fault. While the earth itself has low resistance for high currents, such as those experienced during lightning strikes, it can exhibit significant resistance for low currents. This variance is due to the Earth's resistivity, which is affected by factors like soil conditions, moisture content, and geological composition. In an experiment, it was demonstrated that a low amperage current could flow through the Earth without causing a circuit breaker to trip. This outcome was attributed to the relatively high resistance of the Earth's grounding path. By connecting a conductor directly from a power source to a ground rod and measuring the current using an ammeter, it was shown that the current could surpass the circuit breaker's amperage rating without triggering the trip mechanism. This outcome signifies that the resistance of the Earth, acting as the return path, was high enough to prevent the current from reaching the level necessary to trip the circuit breaker. This finding highlights the importance of considering ground resistance when designing electrical systems and selecting appropriate circuit breakers. In certain situations, the Earth's resistance may be too high to provide adequate fault protection. This scenario can lead to a ground fault occurring without the circuit breaker tripping, potentially creating a hazardous condition. To ensure proper circuit protection, firstly, measure ground resistance. Before installing a grounding system, it is important to test the resistance of the soil to determine if it provides adequate conductivity for the expected fault current. Secondly, use grounding electrodes and conductive materials. Install ground rods, grounding plates, or other conductive materials to enhance the conductivity of the ground path and reduce resistance. Thirdly, select appropriate circuit breakers. Take into account the expected fault current and the resistance of the ground path when choosing circuit breakers. Ensure that the circuit breaker's rating is sufficient to trip at the required fault current level. The Earth's resistance can vary greatly depending on several factors. Soil type plays a significant role, with sandy soils typically having higher resistance than clay soils. Moisture content is another critical factor, as water enhances conductivity. Dry soil exhibits much higher resistance than moist soil. Geological composition also influences resistance, with certain rock formations being more conductive than others. The depth of the ground rod or grounding electrode also impacts resistance. Deeper electrodes generally encounter lower resistance due to more consistent soil conditions and moisture levels. The material and size of the grounding electrode are also important. Copper and aluminum are commonly used due to their high conductivity. Larger electrodes provide a greater surface area for contact with the soil, reducing resistance. Furthermore, the number of grounding electrodes and their spacing affect the overall resistance. Multiple electrodes spaced appropriately can significantly lower the total ground resistance. Ground resistance is measured using specialized equipment, such as a ground resistance tester or earth resistance meter. These devices typically employ a 3-point or 4-point testing method. The 3-point full of potential method involves driving 2 auxiliary ground rods into the soil at specific distances from the grounding electrode being tested. A test current is injected into the earth, and the voltage drop between the grounding electrode and the auxiliary ground rods is measured. From these measurements, the ground resistance can be calculated using Ohm's law. The 4-point winner method is similar, but uses 4 electrodes spaced equally apart in a line. This method is often used for measuring soil resistivity at different depths. Acceptable ground resistance values vary depending on local electrical codes and regulations. In many jurisdictions, a ground resistance of 25 ohms or less is considered acceptable for a single grounding electrode system. However, lower resistance values may be required for sensitive electronic equipment or critical facilities. If the initial ground resistance measurement exceeds the acceptable limit, steps must be taken to reduce it. This can be achieved by adding more grounding electrodes, improving soil conductivity, or deepening existing electrodes. Soil conductivity can be enhanced by adding bentonite clay or other conductive materials to the soil around the grounding electrodes. Regular testing and maintenance of grounding systems are essential to ensure their effectiveness. Ground resistance should be checked periodically, especially after periods of dry weather or significant soil disturbance. Any damaged or corroded grounding electrode should be replaced promptly. In addition to ground rods and grounding plates, other types of grounding electrodes include ground rings, concrete-encased electrodes, and chemically enhanced electrodes. Ground rings are typically installed around the perimeter of a building and connected to the building's grounding system. Concrete-encased electrodes, also known as UFA grounds, consist of a length of bare copper conductor encased in concrete foundation. Chemically enhanced electrodes utilize a chemical compound to improve soil conductivity and reduce ground resistance. Grounding systems are an essential component of electrical safety. They provide a low impedance path for fault currents to return to the source, allowing circuit breakers to trip and clear the fault. A properly designed and maintained grounding system helps to minimize the risk of electric shock, equipment damage, and fire. The National Electrical Code, or NIC, provides detailed requirements for grounding and bonding of electrical systems. Article 250 of the NEC covers grounding and bonding requirements for various types of electrical systems and equipment. The NEC specifies the types of grounding electrodes that are permitted, the minimum size of grounding conductors, and the methods for bonding metal enclosures and equipment. Bonding refers to the practice of connecting all non-current carrying metal parts of an electrical system together to create an electrically conductive path. Bonding helps to ensure that all metal parts are at the same electrical potential, minimizing the risk of electric shock. The main bonding jumper is a conductor that connects the equipment grounding conductor to the grounded conductor at the service entrance. The equipment grounding conductor provides a path for fault currents to return to the source, allowing the circuit breaker to trip. Ground fault circuit interrupters, or GFCIs, are another important safety device used to protect against electric shock. GFCIs detect small imbalances in current between the hot and neutral conductors and trip the circuit if a ground fault is detected. GFCIs are commonly used in bathrooms, kitchens, and outdoor locations where the risk of electric shock is higher. Arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arcing faults. RFCIs detect abnormal arcing conditions in electrical circuits and trip the circuit to prevent a fire. RFCIs are typically installed in bedrooms and other areas where flammable materials are present. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD divert surge current to ground, preventing it from damaging sensitive electronic equipment. Proper grounding and bonding are essential for the effective operation of SPD. Electrical systems should be inspected regularly by qualified electricians to ensure that they are properly grounded and bonded. Electrical inspections can identify potential hazards and ensure that the electrical system is in compliance with applicable codes and regulations. In addition to the NEC, other standards and regulations may apply to grounding and bonding of electrical systems. These may include local building codes, industry standards, and insurance requirements. It is important to consult with a qualified electrical engineer or electrician to ensure that the electrical system is designed and installed in accordance with all applicable requirements. The resistance of the grounding electrode system can be affected by seasonal variations in soil moisture. During dry periods, the ground resistance may increase significantly, potentially compromising the effectiveness of the grounding system. To mitigate this effect, it is important to ensure that the grounding electrodes are installed deep enough to reach stable soil moisture levels. The use of multiple grounding electrodes can also help to reduce the impact of seasonal variations. In areas with rocky soil, it may be difficult to drive grounding rods to the required depth. In such cases, alternative grounding methods, such as ground plates or concrete-encased electrodes, may be more suitable. Ground plates provide a large surface area for contact with the soil and can be buried horizontally in shallow trenches. Concrete-encased electrodes can be installed in the building's foundation or other concrete structures. The selection of the appropriate grounding method should be based on a thorough assessment of the site conditions and the electrical system requirements. The size of the grounding conductor is determined by the size of the largest ungrounded conductor in the circuit. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the ungrounded conductors. Grounding conductors must be made of copper or aluminum and must be protected from physical damage. Grounding conductors should be installed in a neat and workmanlike manner and should be securely connected to the grounding electrodes and equipment. The connections should be made using approved connectors and should be protected from corrosion. The equipment grounding conductor is connected to the metal enclosure of electrical equipment such as panel boards, motor control centers, and junction boxes. The equipment grounding conductor provides a low impedance path for fault currents to return to the source, allowing the circuit breaker to trip. The equipment grounding conductor should be sized according to the NEC and it should be securely connected to the equipment enclosure. In addition to grounding the electrical system, it is also important to ground metal objects that are likely to become energized, such as metal fences, metal piping, and metal building structures. Grounding these metal objects helps to minimize the risk of electric shock if they come into contact with energized conductors. The grounding of metal objects should be done in accordance with the NEC and other applicable standards. The grounding system should be designed to minimize the risk of touch potential and step potential. Touch potential is the voltage difference between an energized object and the ground. Step potential is the voltage difference between 2 points on the ground that are a meter apart. The grounding system should be designed to ensure that touch potentials and step potentials are below safe levels. The use of equipotential bonding can help to reduce touch potentials and step potentials. Equipotential bonding involves connecting all metal objects in an area together to create an equipotential plane. This helps to ensure that all metal objects are at the same electrical potential, minimizing the risk of electric shock. The design and installation of grounding systems should be performed by qualified electrical engineers and electricians. Grounding systems are complex and require a thorough understanding of electrical codes and standards. Improperly designed or installed grounding systems can create serious safety hazards. Regular inspections and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding systems should be inspected periodically to check for damage, corrosion, and loose connections. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. The cost of installing and maintaining a grounding system is a small price to pay for the safety and protection it provides. A properly designed and maintained grounding system can help to prevent electric shock, equipment damage, and fires. Grounding is an essential element of electrical safety and should not be overlooked. The grounding system should be designed to accommodate future expansion or modifications of the electrical system. The grounding system should be able to handle the increased fault currents that may result from adding new loads or equipment. The grounding system should also be designed to minimize the impact of electromagnetic interference or EMI on sensitive electronic equipment. EMI can cause malfunctions, data corruption, and other problems. Proper grounding and shielding can help to reduce EMI. The grounding system should be documented and maintained. The documentation should include a diagram of the grounding system, the location of grounding electrodes, the size of grounding conductors, and the results of ground resistance tests. The documentation should be kept up to date and readily available for reference. The maintenance of the grounding system should include periodic inspections, testing, and repairs. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. The grounding system should be tested periodically to verify that it meets the required performance standards. Ground resistance tests should be performed using a calibrated ground resistance tester. The results of the test should be recorded and compared to previous test results to identify any trends or changes in the grounding system performance. The grounding system should be designed to be accessible for inspection and maintenance. Grounding electrodes and connections should be located in areas where they can be easily inspected and maintained. The grounding system should be protected from physical damage. Grounding conductors should be routed in a manner that protects them from damage. Grounding electrodes should be protected from corrosion. The grounding system should be designed to be compatible with other electrical systems and equipment. The grounding system should not interfere with the operation of other electrical systems or equipment. The grounding system should be designed to be environmentally friendly. The grounding system should not contaminate the soil or water. The grounding system should be designed to be sustainable. The grounding system should be designed to last for the life of the electrical system. The grounding system should be designed to be cost-effective. The grounding system should be designed to provide the required level of safety and protection at a reasonable cost. The grounding system should be designed to be aesthetically pleasing. The grounding system should not detract from the appearance of the building or property.